Cool. Let's get started. Yeah, so last time we talked about... Okay, anyways, so what are we going to talk about today? Today we're going to talk about my favorite topic, which is now we are finally getting into neural networks as ways of doing inference. So inference is a fancy term. What does that mean? What did we talk about last time? Last time we talked about differential rendering. And the key idea of differential rendering was we have some kind of 3D representation, we formulate some kind of differential renderer, and then we can render images that are that we have captured of some real-world scenes. Or we can render images of our scene representation, compare them to images we have captured in the real world, and then we can reconstruct our 3D scene. And we talked about these kinds of different renderers. We talked about volumetric renderers, and that was 2 lectures ago. And then last lecture was a special lecture, which I made on short notice because the paper had just come out, which is 3D Gaussian splatting, and we talked about 3D Gaussian splatting. And I thought that was quite oh my God, what's happened here? Okay, so, but in both cases, what we did here is we did a form of reconstruction, right? We said we had a 3D representation. In one case, it was this neural network or this voxel grid parameterizing our volumetric scene representation. In the other case, it was this Gaussian splatting, like these sparse points, these sparse 3D Gaussian blobs distributed in space, parameterizing the 3D radiance field as well. And in both cases, we could formulate a differential renderer on top, and we could do reconstruction. But what did we actually do here? So we took a set of observations, right? Then using our differential renderer, we could do reconstruction. Let's say, for instance, we would reconstruct a nerve, in which case our scene representation would be like a neural network, right? And then using our differential renderer subsequently, we could render novel views of the underlying scene. So we could split somewhat artificially this thing into 2 steps. The first one is reconstruction, and the second one is then like test time rendering, right? And if you put them into like one framework, it kind of looks like this. We went from images. We did this step here, which was the optimization step. Then we got our actual scene representation. Then we can render it, and then we get novel views. And we talked about this briefly before. What we basically did here is in 3D scenes, or like in our data set, there are a set of observed variables, which are basically the colors of pixels. That's what we observe. And then there's a set of latent variables, which is the 3D geometry and the 3D appearance of the scene. And these are not directly observed. We do not have direct access to the, in other words, we don't have direct access to the radiance field, right? In our data set, we can't go in and I can't ask you at this 3D location, what is the color of that 3D location? Rather, we only have colors of pixels available to us. And so what we did here is, if you like formalized it, you could call it as some kind of inference. We formulated a program by which we could go from these observables, which were the pixels, via optimization, we could retrieve the latent variables, which were the 3D geometry and appearance. So reconstruction / inference. Okay. And last time I ended the lecture with this little example where we said, what if we only have a single image of some 3D scene? So instead of having hundreds of images of some 3D scene, where we can just do this optimization thing, let's say I only give you a single image of this 3D scene. And then I asked you, what would happen if you did the same thing anyway? So I give you the single image, and you try to optimize your 3D scene representation using this differential renderer to fit the single image. And one of you accurately said, like, what would happen is that you would get garbage. Basically, for this one view that you had in your training set, you would get the correct RGB image, but for every other view, you would get nothing. And why is that? That's because, of course, our single image of any scene could be this car, but also, of course, if I captured a single image of this scene and I tried to fit like a Gaussian splatting thing to it, right? The single image doesn't contain any 3D information in itself. Like the 3D information, where does the 3D information come from in differential rendering with many images? That's a question. Why does the network discover the 3D? Enlighten, yeah.
Because it has multiple images and camera poses?
Right, it has multiple images and camera poses. In other words, it basically has to do triangulation, right? There's only, under the renderer that you have formulated, there's only one, ideally there's only one 3D radiance field that can explain all of the images under these camera poses. But if you have a single image, then there's an infinite number of 3D scenes that can explain that single image, which is you can place, for instance, if you think about Gaussians, you could place a little single Gaussian anywhere along a single ray, and the image would always look the same. So only if you have more than one view, you get any kind of 3D information from it. So, but also last time at the end of the lecture, we already discussed that unfortunately, this is the world we live in. Unfortunately, in the real world, you are, as a human at least, never in the comfortable position of seeing a 3D scene that you have to think about from every possible perspective, right? So for instance, if I look at this object here, which is the cap of my thermos bottle, and I want to pick this cap up, right? Actually, what I do is I reason about the side of the cap that is occluded from me. I can reason about this side of the cap, and I know that if I want to grab this cap, like I have a belief over like how approximately the geometry of the cap will look like. But for that, I don't have to observe the cap from every possible angle. So in other words, what I do is I go from an incomplete set of observations, maybe from just a single image or from 2 images, or maybe from like a small set of images, to a approximate 3D reconstruction of this thing that my brain reconstructs. And that's what we're going to talk about today. We're going to talk about different ways of, and surprise, surprise, in order to do that, you need to do learning. This is something that you require priors for. Like I think everyone knows or like is familiar with the word of the use of the word prior. Everyone knows what that means, or like how people usually use that. No, yeah. So basically, priors usually mean you have like some prior belief over what some kind of data could look like. So for instance, you have a prior belief over what cars look like. So I can show you the single image of a car, but you know in fact that this is probably not like a billboard that is like painted in the appropriate colors, but you know that it's a piece of 3D geometry that represents the car. Okay, so today we're going to talk about how can we use all of the things we discussed so far to actually train neural networks such that they can go from a single or incomplete observations to 3D reconstructions of the real world. And today we're going to talk about this is going to be 3 lectures because this is obviously a huge topic. And this is something that is extremely active. So like we do research on this every year at CVPR. There's more than 100 papers on this. It's like a huge thing. There's lots of cool 3D generative modeling, which we're going to talk about. This is very closely related to the task. I want to give you a text query and you want to generate 3D objects from the text query, turns out. Or it's closely related to the task of you just want to train a GAN of 3D faces. So yeah, it's going to be very exciting. Cool. So we're going to start with like a little equivalent thing that you probably are familiar with. So we're going to talk about unsupervised learning. The thing that we're going to discuss is that this kind of thing that we just discussed is going to take the form of unsupervised learning. And why it's kind of apparent, it's because we don't have ground truth 3D scenes. Again, just as before, we only have images. So somehow we want to have an unsupervised way. Just having data sets of images, we want to be able to train neural networks that can reconstruct 3D scenes from incomplete observations. So what is the data we have? We have a huge data set maybe of images. That's all we have. No 3D scenes. Okay, and their camera poses apparently, but like we'll get to that later. Okay, so here's maybe the simplest self-supervised or unsupervised machine learning algorithm that you might be familiar with or that you might have seen before, which is autoencoding. So let's say I give you a data set of images, and now I build a neural network as follows. I build a neural network to take the image as input, and then I build something that takes the thing as input and outputs the same image again. And then I'm going to have a reconstruction loss on top of the output. So this is called an autoencoder. So it's something that autoencodes the image. It takes the image as input and outputs a reconstruction of the image, x hat, and you supervise it just by reconstruction loss in image space, right? Who's not familiar with autoencoders? Good, excellent. Then we can move on. So then you also know how autoencoders usually look like. They usually look something like this. So maybe, because obviously if you just built this without loss of information in the middle, it would be trivial. If you like just had, you just had like a single convolutional layer, that would be this task would be trivial because it would just copy the image, the pixels from the input over to the output, right? That's not a challenge. So the key idea of autoencoders, as proposed in this by Jeff Hinton and other folks, was let's build a bottleneck. So let's build something that let's force the thing to compress the data. So like it has to go from like high resolution to something that is very low resolution. Maybe it just basically the size of a single pixel, but maybe lots of feature channels. And then we're going to train this thing to reconstruct the whole image from this little latent code, right? And then we call this thing, like this thing on the left, we call it the encoder, and the thing on the right, we call it the decoder. And so what is the learning signal here? So why does this learn anything reasonable? Actually, yeah, what is the learning signal here? Why would you expect this thing to do something interesting? Or what do you think would it learn? Yes?
We want the key features already.
Right, so is the hope. So you would hope that it would reconstruct the key features of the image. And now actually, quick question. So is that actually what happens in practice? So who has, what do you think would happen if you took an autoencoder, convolutional autoencoder, and trained it on like all images on the internet? I'm just asking because this is kind of interesting, because I'm sure you've all learned about convolutional autoencoders, right? And so, of course, everyone nods their heads, and everyone is like, yeah, this thing is going to do, it's going to learn something reasonable, it's going to learn to do compression, it's going to learn to do all of these great things, because clearly that's what it has to do. But in practice, what does it actually do? Okay, we can answer the question later, but this is something worth reflecting on. So, like, why does anyone, like, is anyone using these autoencoders today for self-supervised learning? No. In fact, no one's using these because they don't work, right? I mean, that must be the reason at some level of the thing, because they don't work. Something doesn't work. Does no one know or have a guess why they don't work at all? Yes?
Well, I think the latent codes aren't exactly like, I guess they're not like, they're very entangled, so you can't like extract any good information from them.
Right. So, yeah, this is certainly one thing that's happening, so that's good. So I'm not going to answer the question now. It's actually a very long answer, and we don't exactly know the answer yet either. But we do have kind of an idea of the answer, of what the answer looks like, and it's actually very worth reflecting on this as we are going through this lecture. And also for yourself, it's worth reflecting on this. Like, why doesn't this just work? Like, clearly we have deep learning magic. This should just work, but of course it doesn't. So otherwise we'd be done, right? Otherwise we'd be done with computer vision. We just do this, and then we would have the perfect self-supervised learner. We just train it on all the data on the internet, and we'd be like, yay, here's our vision model. But we're standing here, so this clearly doesn't work. Just something to keep in mind. Okay, good. But yes, that was the motivation, and it does work to some degree, right? So you can train this, and in fact, it is true that what you find is that this latent code has information about certain things you might care about. So for instance, maybe, potentially, you could find that the latent code is correlated with some semantic classes in the image. So maybe it would tell you that there's a fish in the image, or it would tell you that there's corals in the image, or something like that. And in fact, on very simple data sets, it really does work. So if you take MNIST, which is like this data set of little digits, you can see on the left, which, fun story, MNIST was actually collected for a real-world task, which was OCR on letters. So like, this was one of the first neural networks that was actually deployed, was a neural network that does letter recognition, like, how's it called? OCR. Yeah, thank you. Optical character recognition for letters that people sent around post offices. It was the first convolutional neural network, to the best of my knowledge, that was deployed at a large scale. So this had a very real-world motivation. But anyways, like if you train a autoencoder on this task, you can actually find, if you cluster these latent these latent codes according, like with tsne or PCA or something, you can actually find that these single letters really do show up. So it kind of really works. Okay, so now we're gonna, so any questions to autoencoders, other than why they don't work, apparently? Okay, good. So then we're gonna now shut this equivalence, and we're gonna move on to 3D scenes, and we're gonna build something equivalent just for 3D scenes. Okay, let's build a little toy data set. And this is actually where the field was in 2019 or 2018 when I did my PhD. So these are the slides from my paper, Scene Representation Networks, that I wrote back then. And this is, in fact, the data set that I rendered and used. So let's say we built a little toy data set. We have a set of 3D scenes in our training set. Let's say, for instance, our 3D scenes would be these toy cars from ShapeNet. And now we assume that for each of these 3D objects, which we don't want to train on these directly. Our assumption is we don't have access to ground to 3D scenes, because in the real world, we don't have access to ground to 3D scenes. So we don't assume we don't have access to that. Assume the only thing we have access to are renderings of these 3D objects. So for each of these cars, imagine you have 10 or 20 images of that car together with its camera pulse. So maybe, in fact, for each of these cars separately, you would even have enough information to reconstruct the car by itself. Think about it like that, but that's not necessary, but imagine like that. So like imagine for this car, you had like, I don't know, 20 images, and you could like reconstruct a nerve, for instance. Okay, so that's going to be our training set. And now the question is, what can we learn, or how can we learn something about the 3D scenes given these image observations? So how can we, in other words, learn train neural networks that learn something about the underlying 3D scenes, even though they only look at the images. And this is what we've been building towards. So this is the answer that now we can, this is the question we can now answer with all of the preliminary work we did. So let's build the dumbest possible baseline, which actually turns out, in retrospect, as we're going to see later, it's maybe not all that dumb, but we're going to build a dumb baseline. So we're going to take an input image. We're going to basically build an autoencoder. We're going to encode it with a convolutional encoder. Going to give us a little latent code, just like in the autoencoders before. This might be like a 256-dimensional latent code or something like that, right? And now we're going to build a convolutional decoder, and what we want is that this convolutional decoder renders a novel view of the underlying car. Okay, so we give one image of the car as input, and then we ask the thing to render a different view of the same car, which is fine because that's in our data set, right? No problem. And in order to specify which view, we're going to also, in the latent space, concatenate maybe the pose of the camera view that we want to render. So for simplicity, assume for a moment that all of the cars were oriented in the same way. So all of the cars, like the cars live in a coordinate system where the x-axis points like in this direction, and all of the cars are oriented along the x-axis. So the same camera pose always corresponds to the same perspective of the car. And so this is the pose that we would then concatenate here. And you could, of course, also in theory concatenate the camera intrinsic parameters, right, if you wanted to be complete. But let's just say all of the camera is always the same camera. It's always okay. So you can train this thing. And this is, in fact, from a paper, which was, I think, ahead of its time in 2015. And this is now our autoencoder. Just exactly as before we trained an autoencoder on images, this is still an autoencoder on images. Just now, instead of just autoencoding the same image, in a way, this is now autoencoding 3D scenes, right? And in fact, at the end of this, you can, how do you train this? Well, you just train it by a training time, giving it one view, asking it to render a different view, and then supervising it with the ground truth view that you have of that object, right? Cool, so let's train that. So if you train this on 2,500 ShapeNet cars, and this is what it looks like. So what do you think? I mean, kind of, I would say it's, so these are test, I should also say, these are then test objects, so these are cars that it hasn't seen at training time. So I would say it's not like terrible, it's kind of, it kind of has gotten like some critical information about each of the cars, but I mean, clearly there is like, clearly this is far from ideal. Okay, how can we maybe fix this? So one way to interpret this is that this model hasn't actually discovered true 3D representations, right? Like if these objects were two 3D like things, if the model would have in the latent code actually encoded the 3D geometry and appearance of the thing, then one could hypothesize you could render each of these cars perfectly. Maybe you wouldn't, if I give you a single image of this car, maybe you wouldn't reconstruct exactly the same car because maybe you haven't seen the back of the object or something, but you would expect that at least for the points that you have seen, those you should be able to render perfectly. Does that make sense? Okay, but that's not what's happening. So something's broken. So, okay, let's skip this. Okay, so this was the situation I was interested in. So let's put this into a framework that we're familiar with. So here's an interpretation of what's happening. We could say that we have our input image. So we could say that the latent code, the same thing that in the autoencoder represented the image clearly, is now our scene representation, right? This is the thing, just as before we were talking about voxel grids, we were talking about neural fields, we were talking about all these kinds of 3D representations. You could now say, well, this latent code is the thing that encodes theoretically all the information about the 3D scene, right? And then you can say, well, our renderer, the thing that implements the rendering function, which is the thing that takes the scene representation as input and maps it to an image rendered from a novel view. Our renderer is now basically this convolutional decoder, which who knows what that does, together with the input pose. We give it the input pose and the scene representation is input, and then it produces that view of the thing, right? So this is just putting it into the boxes that we know already. Does that make sense? Great. Okay, so now let's see, how could we do a better job at this? With the things we've learned in the past. I hope you paid attention in the past. How many weeks? I don't know, 8? Yeah. So how could we build something that is guaranteed to render things, that is guaranteed to learn 3D representation? Okay, so the idea would be, well, we already know what a renderer looks like. We already know what a differentiable renderer looks like. We've built them a bunch of times. So why would we use like a learned renderer here? Let's just use a renderer that we know actually what it does, and we know that it follows the rules of 3D geometry and appearance. And then let's put into this box some kind of scene representation that we have discussed before, and we've discussed a bunch of them, right? Voxel grids. Okay, good. So what would that look like? Okay, actually, let's keep it here. So does that make sense? So like now what we're going to do is we're going to take an image, we're going to build some kind of encoder. In this case, it might be a convolutional encoder. And then conditioned on the image, it's going to output somehow, we don't know how yet, it's going to output our 3D scene representation. And then we're going, instead of just having a latent code and sticking that into a convolutional decoder, we're going to use this 3D scene representation and we're going to render it using the algorithms we already discussed. That whole thing is end-to-end differentiable. So we can use exactly the same data set, but now when we train our model, we know that at test time, our model will give us 3D representations. We know all of our renderings will look reasonable. So this seems like a big win. Make sense? Great. Okay, so how do we actually do this? The key question, like we already discussed what is a box scene representation and a box differentiable renderer. So these questions are kind of answered seemingly. So the key question now is, how would we build something that goes from input image to this 3D representation? So, and of course that depends on what kind of 3D representation you pick. So like, for instance, you could pick a voxel grid. So you could say, okay, I'm going to go have an image as input. We're going to somehow have a convolutional encoder, and it's somehow going to output a voxel grid that we're then going to render, right? That might be one thing. Fundamentally, the thing that you won't get around is fundamentally you'll just have to, whatever you pick here, you'll have to predict all of its parameters as the output of the convolutional encoder. So if you commit yourself to predicting a voxel grid, one way or another, you'll have to build some kind of neural network that outputs a voxel grid. And voxel grids are obviously pretty big. So this is, for instance, like a significant commitment. You could also pick something else. Maybe you could pick a triplane. Remember these triplane representations that we discussed? So instead of having, a voxel grid where every voxel stores the information there, maybe you have these 3 planes. And so you could instead predict the parameters of a triplane. Triplanes have much less information, have much fewer parameters than voxel grids, right? Voxel grids have a number of parameters that is cubic in the resolution. These triplanes get a little complicated, but you could first order say they have a number of parameters that is like quadratic in the spatial resolution that they encode. Okay, that seems better. Or you could say, well, maybe we're predicting neural fields. So, and just for the record, neural fields were these, right? That's like a nerf, for instance, okay. But in a neural field, what are the parameters of the scene representation for a neural field? Yes? It's just the weights of it's the weights of the neural network. And the weights of the neural network is also a pretty big thing. Okay. But for a moment, so it turns out the question that I'm just asking you, so flippantly actually is like a whole thing. Like, how do you build these encoders and how do you output these things is like a whole study of research, which also touches on topics like geometric deep learning, which we're going to touch on later. So this is something that requires a lot of care and a lot of thinking. So for now, we're just going to go back to me when I was my PhD, like Vincent as a stupid PhD student who doesn't understand how the world works. And we're just going to go through that thought process. And we're just going to do what's right, what sounds right for a moment. And that's actually perfectly fine. That's a perfectly fine way of doing research. At least from my perspective, it has worked. I don't know, maybe your mileage may vary. Okay, sorry, why did it skip backwards? Okay, so let's just, okay, so like we have committed ourselves. We just said, okay, we're just going to predict all the parameters of our scene representation. So, okay, whatever. Let's just build something and see if it's at all tractable, and we're just going to do it. Okay, so here's something you can do. Forget about this. What we're going to do, for instance, is we're going to. So yeah, this is kind of an architectural detail, but okay. So let's say that's what we want to do. Let's say for a moment we pick as our scene representation a neural field. So the neural field, the parameters of the scene representation is all the weights of the neural network, like the weights and the biases. So that's the parameters of the scene representation. So somehow we have to build an encoder that goes from the image to all of the parameters of our neural network. So for simplicity, let's say that we're going to go the intermediate step of a latent code. So we're going to do the same thing as with the autoencoders. So we're going to have our convolutional encoder. It's going to output a latent code. And now the only thing we have to invent is the way of getting from the single latent code to all the parameters of our nerve or of our neural network, right? Okay, let's build that. So what are we going to do? This sounds like weird, but okay, let's say we wanted to predict a neural field. One thing you could do is you could literally do like the deep learning thing, which is I don't know anything about anything, so I'm just going to say we're just going to build a neural network, and that's going to take the latent code as input, and it's going to output all of the parameters of our neural network. Totally reasonable thing to do. It even has a name. So people gave this a name, which they call it hyper networks, which is kind of weird. You should have called it meta networks. That would be more consistent with like related work, like meta learning and so on, but they didn't. They call it hyper network. It's a great paper. But okay, so this is. I think even in PyTorch, this is not hard to implement. You could literally do this, right? So like the parameters of this neural field, these are just weight matrices and biases. So now you would just pick some network architecture up front. You would say, okay, I have 4 layers. My nerve is going to be 4 layers, 512 hidden units. So I'm just going to have to predict 4 times 512 squared plus 4 times 512, which weights and biases of my neural network. And so I'm going to build like a neural network that takes the latent code and just outputs all these parameters as output. Does that make sense? Is that okay? Good. So there's nothing interesting. There's basically, so to speak, nothing interesting here. It's just you would do exactly the thing that. Okay, you do the obvious thing. So yeah, this is what we're going to do. We're just literally going to take a neural network that takes the latent code as input and outputs the neural field parameters. Okay, so let's say we wanted to instead pick a voxel grid as our scene representation. And this is now actually starting to get interesting. So if you pick a voxel grid, what would you use as the network that predicts the weights of the voxel grid or the parameters of the voxel grid from the latent code? So let's say I give you a latent code which has, let's say, 512 dimensional. And now I tell you I want you to build a neural network that takes this 512 dimensional latent code as input, and it predicts a voxel grid with side length 256. And I don't know, 4 parameters in each voxel. What would you build in the box? What would you put in the box in between? Has anyone heard about 3D convolutional neural networks? Who has heard about 3D convolutional neural networks? Okay, not everyone. So I guess this is not something you learn about. So what I'm getting at here, so like the reason why we're discussing this is because we're hinting at some subtleties that will arrive later. Right now, I'm trying to communicate that for different choices of these scene representations, there are different ways how you could build the algorithm that goes from latent code to these scene representation. And for now, we don't understand how they are different, but it's worthwhile to just point out that there's different ones for different scene representations. Because for later, we'll notice that it matters a big deal. So let's say, for instance, so if you had a voxel grid, so who knows what deconvolution is in 2D convolutional neural networks? Like, when you build this, previously we just talked about the autoencoder, right? So the decoder part goes from a latent code with resolution like 1, for instance, right, to like an image. How do you do that? You do that with like a thing which is called a transpose convolution. We're not going to talk in depth about it, but basically the idea is you build a convolution that instead of like when you want to lower the resolution of something, you build a convolution that basically skips something in the input, right? It has like a stride, for instance. So you take an image and then you do your convolution, and it's going to only look at every third pixel. And then in that way, you can half the resolution of the output. And there's basically the transpose, kind of a bad name, but like there's basically the inverse of that, where you can build a differentiable layer that takes like an image of resolution h by height by width as input and outputs like an image with a resolution 2 times height, 2 times width. And these are called deconvolutional neural networks or transpose convolutions. And the same exists in 3D. So, but most of you must have implemented something like this before, right? Like, or like who has implemented an autoencoder before? Okay, so then you know what transpose convolutions are. Okay, good. Just making sure. Okay, so it's worth noticing if you pick the voxel grid as a scene representation, then you would have a different architectural choice. You could again do the same thing. You could just forget about the structure of this voxel grid as a grid, and instead you could just say, I'm going to view my voxel grid as an unstructured list of parameters, and then you can do the same thing that we just did with here, right? You could again build like a fully connected neural network that will take the latent code and it just outputs all of the parameters of the voxel grid. But it is worth noting that in this case where you know you have a voxel grid, there's suddenly another architectural choice to you, which is a deconvolutional neural network. So let's keep that in mind. So here's another thing you can do for neural fields. I'm just mentioning this. Instead of building this hypernetwork, which basically takes this latent code as input and outputs all of the parameters of your scene representation, you could also say do something like slightly weird. You could say, well, my scene representation is already a neural network. So this is like, let's say, my nerve. And my neural network, I can just, so right now it takes three inputs. It takes the x, y, z coordinate as input, right? But maybe I can just extend the input and I say it also takes the latent code as input. So I'm just going to give it the 3D coordinate, and I'm going to give it the latent code that represents the underlying object. And then I just pray that my neural network will learn, when I train it, to basically listen to the latent code and decode the correct car. And in fact, that kind of works. I think that's actually what you're going to implement in homework number 3. So that's another way. So you don't actually have to predict all of the parameters. It turns out that this is actually, if you do the math, it turns out that this is actually equivalent to predicting the parameters of only the first layer. So this is actually identical to the previous case, where you're just predicting the parameters of the first layer, like the weight matrix and the biases of the first layer. But it's not particularly important. So it's worth noticing that this is something that papers were written about, like 2 years ago. People really, like, in retrospect, much of this seems silly, but much of research seems silly in retrospect. As we'll learn later, none of this really matters all that much. But when you read papers from the last 3 years, you'll come across all of these words, and you'll come across, we do conditioning via concatenation, which is what they mean here. They condition their scene representation on the latent code by concatenating it to the input. It has a name. People gave it a name, conditioning via concatenation. The other thing people will call a hypernetwork, and then so you'll read these words, and they correspond to some simple concept. Okay, does it make sense? So far, we're only talking about different ways. If you can take your latent code, about different ways how you can then use that latent code to parameterize your 3D representation. Questions so far? Great. Yeah, let's skip that, whatever. Okay. There we go, so skip that. Okay, so here then is going to be our general framework that all of these methods that we're going to talk about in a moment actually fall into. And this is, in fact, still how it's done today. So like, this is just the way, this is like a relatively general formulation. This is actually the way it's going to work. The way it's going to work is you're going to take some kind of, you're going to take images as input, a set of image observations of some 3D scene. Then you're going to build some kind of encoder. This is going to be a big neural network. Could be really big. Okay, and then what that neural network is going to do, it's going to predict a set of features or a set of latent codes. Could be a single latent code, as we just discussed. Could be a set of latent codes, like hundreds. Could be a grid of latent codes. Could be all kinds of stuff. And then you're going to basically, in some way, shape, or form, decode these latent codes into a 3D representation. Either you decode them into a voxel grid, or you decode them into a neural field, or whatever. And then you're going to stick that into a neural renderer, and then you can render the thing that pops out, and then you can train this whole thing end-to-end on your training set. Does that make sense? Great. So here's the thing that we're going to be talking a lot about for the next several lectures. So one question is, what are these latent codes? Like, what information are they going to encode? What can we actually learn? And how many should there be? And like, does it matter? Like, what architecture we pick? All of the things we just discussed, why do they matter? Why does it matter if I pick a voxel grid or a neural network? The other question is obviously like the inference algorithm. So the encoder, the thing that takes the images as input and outputs these latent codes. Do we have to be careful when we design that? Does it matter? Should we just build a black box? Should we build something careful? The answer is we, of course, have to be careful, as always. And then this decoder and this neural renderer, what kinds of different short forms can that take related to the thing that we also just discussed about, and so on. So this is basically what we're going to be talking about for the next several lectures, and this is also what all of the generative models, 3D generative models fall into. So this is actually all the same framework. Okay, so here's, so now we talked a lot about like different definitions of stuff. Here's now, I'm just going to walk you through training one of these models now, okay? So we're just going to actually build one of these models now, and we're going to train it. I mean, you're not going to literally build it. I built it in the past, and I'm showing you what it looks like. So here's a specific thing we can build. This is related to what we just discussed. we're literally going to build this model. So take an input image, encode it with a convolutional encoder, get a single latent code out, decode it into the neural field via hypernetwork, do sphere tracing as our rendering algorithm, and render the image and train it end to end. So you can literally just train this. You should know each part of this now. So here's the data set. The data set is a data set of lots of cars. So for each of the cars, we have many observations of the underlying 3D of that car. And now we can train this thing end to end, right? Is there any confusion about how to train this thing still? Or can you imagine what all of the parts look like? If I asked you to implement this right now, would any questions come up?
When you said hypernetwork, are you referring to the concatenation?
No. In this case, what I implemented, that would also work, and it would yield very similar results as the ones we're going to look at in a moment. But in this case, I built this thing that takes a latent code as input and outputs all of the parameters of like a neural representation. So in this case, the neural network was like 256 hidden units and like 5 layers. That was the neural scene representation, like a neural field. And in this case, the neural field decoded into a signed distance function and a color, like the thing where we discussed the sphere tracing algorithm. So the renderer was a sphere tracing algorithm. The scene representation was a neural field. And the way we predicted the neural field from the input was encoder, output, latent code, predict all the parameters of the neural field. Okay, good. So here's what it looks like. Now, at test time, we can take the single image as input, and our convolutional encoder will give us a 3D representation. And it doesn't loop. And then we can render the scene representation from arbitrary novel views, as you can see here. So let's look at that one more time. So this is really at test time. There's no optimization necessary. This is a single forward pass. So from the single image, we took our convolutional encoder. It looked at this image. It produced a latent code. The latent code was used to parameterize a neural field, and then we can render the neural field using sphere tracing. So these are the renderings of the car that we just reconstructed from a single image. Compare that to the thing that we looked at last week, right, where we just tried to reconstruct it via gradient descent. That didn't work, right? So now here we are. And now if you look at it, it looks fine. It doesn't look amazing. It's like not great, but it's like better than we were before. So now we can do better than that. But as a first step, it's pretty good. Yes?
Did you train it on just cars, or
yeah.
Train it on like different types of objects?
This model was trained just on cars.
So you sort of enforce some inductive bias on what like a car should have, like windows and like is that really
yeah, so you're not literally enforcing anything. Like the only loss that you're training for is an image reconstruction loss. But yeah, intuitively, what this model learns is it just basically learns to, it learns kind of like what a prototype car looks like. And then it basically takes the image and it just projects the image that it sees onto what the prototype car looks like that it has learned. And so it just, yeah, a fair way to think about this is it's kind of deforming the prototype car that it has learned. And in fact, if you remember the discussion of the neural tangent kernel that we discussed before, do you remember? Does anyone remember what we discussed there with the neural tangent kernel shenanigans, where we said that a neural network kind of interpolates the training set? So without going into too much detail, you can actually imagine that something similar is happening here. So what this model will actually do at test time, it's like a little bit complicated because now, of course, this model has many moving parts. It has this convolutional encoder and it has all of this other stuff. But really what this model is doing is it's kind of retrieving in its training set the cars that looked most similar to this car. And that probably includes things like color. It probably includes things like silhouette and so on. And then it kind of interpolates the cars that it has seen and kind of tries to make it kind of look like that. That's kind of what's happening, if you wish. And so let's actually talk about this a little bit more. So should we talk about that now? So maybe the thing that is not quite obvious is that what this model learns to do is it learns to kind of interpolate between 3D cars. So right, like what this model does is it explains the 3D car as an interpolation of 3D cars that it has seen at training time. And why is that noteworthy? It's noteworthy because apparently the input to this model was just these images. So So apparently the input of this model was just the images, but somehow this model has discovered by itself the 3D geometry of these objects, right? And actually maybe this is really not obvious, right? Like it's not obvious that this model should discover by itself what these 3D cars look like. And so the reason why I did that is because we built this differentiable renderer together with this 3D scene representation, which what it basically enforces is it constrains the set of possible explanations that the model can find for the training data. So in the training data, there's all of these images of cars. And now what we have told our model is whatever you do, each of these images, you can only explain it by reconstructing a 3D car that renders to that image. You can't explain it in any other way. And that's what forces the model to discover this latent space of 3D cars. So each latent code in this model now, when you sample a random latent code, each latent code will map to a different car. And you can walk around in the latent code, and it'll decode into different cars. Okay, so here's a funny thing. Yes?
Given like what typically happens with autoencoders, I'm surprised that you can like interpolate in the latent code space. Having an intuition as to like why the latent codes here have some of the
So the question was like, why can you interpolate in this latent code since autoencoders kind of are bad? So first of all, you can interpolate in latent spaces of autoencoders just fine. So if you take NList and you train an autoencoder on NList, you can totally walk around in the latent space and you can see the digits morph into each other. So the reason why autoencoders don't work, and it's interesting that no one here tried this because that, what actually happens when you train an autoencoder on like large data sets of images? Like what do the outputs of the autoencoder look like? Right, it's just a blurry mess actually. Like has no one actually really tried that? Like, so I really encourage you to play around with this kind of stuff because it's actually really how it's kind of important to understand and build into intuition for this. So if you train an autoencoder on ImageNet, for instance, what's going to happen is that the outputs of the autoencoder are just going to look complete garbage. Like if you train it on like large distributions, like if you train it on NList, it works. If you train it on these cars, maybe it works. If you train it on ImageNet, it's not going to work at all. It's just going to give you utter garbage. Like each of the images that it reconstructs are basically just going to be blurry messes of like, okay, I saw, like, let's say there was this image of the fish before. There's going to be like an orange blob where the fish was. And then there's going to be maybe another yellow blob where the corals were, if you're lucky. And other than that, it's just going to be complete garbage. So the reason for that is basically that it's not that you couldn't compress that image into that small latent code. You could, in fact. There's almost certainly a compression algorithm that takes that image as input and compresses it into a similar latent code of similar size that looks much better than what the autoencoder found. It's just that the autoencoder never found that solution in the first place. It could have found it by deep learning magic, but it didn't because it's not good as an architecture. Okay, but that's kind of so long story short, if your autoencoder does reconstruct all of the objects well, which is the case in this one, actually the latent space usually is fine. So the challenge of autoencoders comes not from the latent space being bad, which can also happen, but usually it comes from them just not doing the thing in the first place. Like they're not even good at autoencoding. Yes? Great question. So do you mean for this model in particular or when you train it on ImageNet or something? In general, yeah. So the question is if you take an autoencoder and you train it on ImageNet or like on like a large data set of images and you make the latent space really large, does that fix the problem? Is that a fair free formulation? The answer is no. Even if you make the latent space really large, the autoencoder will still not discover a sufficient explanation. At least when you build a now I'm starting to give hints. At least when you build a convolutional encoder, it won't. But yeah, good question. Keep that. And we will discuss why in actually this lecture or next lecture, depending on how far we get, or we will discuss some intuition for this. Cool. Any other questions? Yes? No? Just scratching the head. Good. Okay. So what do you expect to happen now if we give this model? Oh yeah, a piece of information missing. This model was trained on images of cars that always had this distance. So like they always saw like they always were on the views in the training set were sampled. Sorry. the views in the training set were sampled from a sphere. So the views were always on the sphere around the car. So they have always seen cars that kind of from that distance. What do you expect to happen if you give it this input view? What do you think will the model do? Right. So we would call this like exactly. So this is an out of distribution input, right? So it's out of distribution in the sense of like very formally we can say we have a distribution of input views that our training set follows, and this one is out of distribution. So in fact, it could either be a really big car that is like sampled from the same thing, or it could be like the same size car zoomed in. And it's actually the latter in this case. But if you try to reconstruct this is what the model gives you. And it's kind of cute, if you're being honest. I mean, it looks kind of like a little Humvee, but as you can tell, it's like not quite what we're aiming for. So what did the model do? What the model did here is because we trained it only on cars, it's it projected whatever it sees, right, on the training set and on the training distribution, I should say. It basically projected it on the training distribution. In the training distribution, there were only cars, of course, because as we said, that's the only thing in our training set. There were only cars that were around the origin with a fixed size. So what the model did in this case, it just picked the biggest car in its training set because that one had the one that most closely matched the silhouette, right? And then it just gave you that. It's like, here, that's the best I can do. Anyway, so how could we fix this? One way we could fix this, of course, is we could augment our data set. We could just also include all of these views in the training set. We just render more views, or hopefully, if you're lucky in the real world, we have all of these views already. Unfortunately, of course, we generally don't. And so, you know, this sounds like a super toy example, but here's an unsolved problem in computer vision. And when I say unsolved, I literally mean unsolved. No one knows the answer to this right now, okay? So how is it that when I show you an object, let's say I give you this mug, and I put you in a room, and I blindfold your eyes, I put the mug in front of you. I take your blindfold off, you look at the mug. I put the blindfold back on, I take you outside of the room, I take the mug with you, and now I put you somewhere, and I put the mug really far away. Without fail, right, you will recognize that mug. Right, you'll be like, yeah, that's the mug I just saw. Even though the view that you're getting from this mug is hella out of distribution. You saw this mug from one angle and from one distance, but your brain don't care. Your brain is like, okay, yeah, same mug, it's just smaller, which means it's further away, right? So this is in fact what we're simulating here, right? This is in fact what we're doing. Our model here gets this, and in this case, to be fair, this model, there's no possible way this model could have discovered this because we never varied the distance at all. So it would indeed be very surprising, but I'm just pointing out this is not a toy problem, and even in the real world, this is kind of a problem that modern models have. Like modern models do not generalize to out-of-distribution views. Like even the 2D ones, if you take Dino or something, or like any of these 2D vision models, and you give it a perspective that it has never seen before, it probably won't do a very good job at it. So unsolved problem in vision. We don't know how it works. Anyways, here is one way how you can solve it, and this is kind of a slight tangent, but not that much. It's now mixing two things up. So, what have we used our 3D set representation, our renderer for in this case? We really used it as a decoder, right? Like we basically replaced this convolutional decoder, and we replaced it with our 3D structured renderer and our 3D structured scene representation. So. You could say all of the heavy lifting with respect to reconstruction is actually done by the encoder, right? The decoder is just rendering the thing. The decoder is the thing the encoder is the thing that has to go from image to latent code. And the latent code actually represents the object. So the encoder is doing all of the heavy lifting here. And the encoder fails in this case because the encoder is a convolutional neural network. The convolutional neural network doesn't generalize to this perspective, and so it doesn't know what to do. Okay. So it turns out we can do a little bit better than this. We can build a different inference algorithm in this very specific case, but also more generally, we can build a different inference algorithm, so a different way of reconstructing the latent code, such that we will be able to reconstruct this view, this out-of-distribution view. And that's what we're going to talk about now. So this is a little hard to explain, so please feel free to interrupt me. I've explained it many times, so one would think that by now I'm better in it, but so yeah, please feel free to interrupt and ask questions, okay? It's not that it's inherently so complicated, it's just because it throws out many of the intuitions about how deep learning works that many folks have. Okay, so here's a funny little thing we can do. We can take our training set. So this is, This is our training set. And so notice here, so each of these sets here is like observations of a single car, right? So top row is this police car, second row is this other car, okay? So now what we're going to do is we're going to do something slightly different. We're going to say that already at training time, each of our objects in the training set, or each of our 3D scenes in the training set, we're going to assign it a latent code. We're going to randomly initialize a latent code. Like, we pick some hyperparameter, we pick 512-dimensional latent codes, and for each car in our training set, we're going to assign it a 512-dimensional latent code that is randomly initialized. Okay? So far, so good. Now what we're going to do is we basically build only the decoder part of the architecture that we just discussed. So we're going to throw away the encoder. Before there was this convolutional encoder, we're going to throw that away now, and we're going to build something that just only is the decoder part. So we're going to take our latent code, and then this latent code, we're going to map it to a neural field. Could be NERF, sorry, SRN, by the way. This is Scene Representation Network. These slides are from my old paper. But imagine this was just NERF or like any neural field. This is just a neural field. And this is the hypernetwork. So this is just one way of mapping this embedding to the weights of this representation. You could also concatenate it to the input, any of the things we just discussed. Okay, so far so good. And then you just build your render on top. And now what you're going to do at training time, you're just going to loop through your training set. And I'm just going to animate this one more time. At training time, you're going to sample an image from your training set. Like, let's say we picked that image of the police car and its corresponding camera pose. And you're going to pick the latent code that you assigned to that object. Then you're going to do a forward pass through this model. So you take the latent code, you do a forward pass, you get your neural field, you render your neural field, you get your image. And then you enforce the loss on that image. And now, when you do the backward pass, you actually backpropagate into all the weights of this model. You backpropagate into the hypernetwork, you backpropagate into the latent code as well. So you're jointly optimizing the latent code together with the weights of the hypernetwork. Hypernetwork is like so super complicated. With the weights of all the neural networks involved in this thing, right? So it's like, I don't know, this is like, I should get rid of all this math. There is no math here. It's like, you just take embedding, you get the scene representation from it, you render it, you get the image. You enforce the loss, you backpropagate it into all the weights. You literally PyTorch training loop, you just like optimize, atom, hit, go. Okay, good. You just train this until convergence. Does that make sense? Good. So now, what do we do? Okay, so this is training time. What do we do at test time? So at test time, remember, at test time, I'll give you an image of a new car, an unseen car. You've never seen this one, unfortunately. And now what do you do? You're going to randomly initialize a new latent code. You're like, okay, don't know. Maybe you initialize it all zeros or something, right? Okay, and now you're going to do the same thing again. You're going to do a forward pass through your network, and you're going to render that view of that car. You're going to enforce a loss, but this time you're going to freeze all the weights of your model except for the latent code. And then you're going to backpropagate into the latent code only. Okay, so let's intuitively, what do we do? What are we doing here? Intuitively, we're saying at training time, we're learning a model plus a latent space. We're learning a latent space of all cars in our training set. Plus, we're learning a model that takes this latent code and decodes it into a car, right? We're training these two pieces together. At test time, we're saying, okay, now we have our model that maps latent codes to cars. That's done. We're going to freeze that. We don't optimize that anymore. All we need to do now is we need to do inference. We need to do reconstruction. And reconstruction means we need to just find the latent code. Given a car, latent code. Previously, we did that with the convolutional encoder, right? We took the image, gave it to the convolutional encoder, done. Now, we do it by this little optimization algorithm, right? Any questions? Yes?
So this is just some way of like replacing the encoder with like basic of your decoder.
Great, yes.
So you have flexibility.
Yeah, you should give the lecture. That's actually a much better way of putting it, yes. So that's how I should have started. So the trick was, now what we're doing is we're, exactly. So instead of doing, like previously the inference and the rendering were two separate things. Like the inference was done by this convolutional encoder, and now the rendering was separate. And now we're just saying we're going to use the decoder for inference as well. And this is in fact called auto-decoding. This has a name. People don't use it very much, but I think that some people use it still, and there's like really cool theoretical guarantees, as we're going to see in a moment. But this process is called auto-decoding, just like auto-encoding, where you do it. So now it's called auto-decoding. Great question. Other questions? Yes?
So we're still thinking about our leading code as like our scene representation, right?
Yeah.
And so in this way, like how traditionally our nerf is our scene representation, during inference time, we can like optimize our scene representation just from.
That's correct. Yes?
Yeah, maybe you'll talk about this next slide, but I didn't get the intuition for how that would solve the scaling there.
Great. Yes, we're going to talk about that now. Okay, so a few fun things before that. Before talking about how it solves that problem, here's a few fun properties of this thing, which are also not obvious. So when you build a convolutional encoder, the encoder that you're building, always at test time, you always need to have an image, right? Like if you want to do inference, you always need to give it the image. And in particular, the image, like modulo some tricks, always has to have the same resolution, for instance, right? If you train your encoder at a resolution of 64 or like 128, and now you give it an image with a resolution of 32, that's not going to work very well, right? So here's the fun thing about this whole thing. Because this thing doesn't have a convolutional encoder, this thing can be trained with single pixels. Because like what is the loss formulated on? The loss is actually from each pixel in this thing is independent. Each pixel is rendered independently from everything else. So in fact, if I gave you an image where like you only had a few pixels of the image, you could still do exactly the same thing. You could take these few pixels and you just minimize the loss for these few pixels for whatever you have, and the model will be perfectly fine with that, and it'll just do the thing, right? And so the samples do not need to lie on regular grids. So it's resolution invariant. So that's just a fun fact. Okay, so now how does this solve our problem? Okay. First of all, let's see what the difference is if you do inference with these two methods. And the answer will disappoint you a little bit. But so first of all, let's look at these two cases right here. So here we have zoomed out and zoomed in. And if you do inference with our convolutional encoder, it's going to look like that. So it explains it with very small cars and very big cars. But now if you do inference with our new thing, it's going to do something much more reasonable. And why is that? The reason for why this works is that you could say we cheated a little bit, but we actually didn't. But like, what is the difference between this inference algorithm and the previous convolutional encoder? Maybe someone knows the answer. Why does this work, and where the other thing failed before? So the reason is because we could use the camera pose, long story short. Before, when you had your convolutional encoder, the convolutional encoder just takes the image as input. The encoder has no understanding from what angle that image was captured or where the camera was when that image was captured. When we do the thing that we just discussed, note that the inference algorithm makes use of a piece of information that the convolutional encoder cannot make use of, which is the camera pose. Basically, what we did here is that we at inference time, we got the camera pose that this object was captured with, which is a strong assumption, but like, and then imagine we placed the camera really close to the object. And now we optimized this loss. The renderer, right? Imagine we were using volume rendering as renderer, right? The renderer doesn't care how far it is away from how can I explain this? The renderer doesn't change, right? The renderer is still, you take the samples along the way, and then you integrate them. So the renderer is actually invariant to like where you place the thing. It'll just do the right thing anyways. So from the perspective of the renderer will just render the car from closer. Okay, yeah, this is a better way of explaining it, sorry. So the best way of explaining it is, it's obvious that at test time you can render novel views, right? Including those where you move the camera closer to the car, right? That works. So you can render views that you have never seen before at training time. And for the same reason that works, the inference also works. Because you'll just move the camera closer to the car, and then you'll just backpropagate into each of the pixels. And now the renderer basically just backpropagates the signal into where it belongs in the 3D volume, where previously the encoder didn't have any notion of, from that perspective, the image was captured from.
But if you gave the camera pose to the convolutional model too, then would it?
No. Good question. What would happen if you gave the convolutional encoder the camera pose too?
Or maybe not to the convolutional model, but maybe to the renderer itself directly.
How would we do that? We're already giving the camera pose to the renderer, right? That's how we are rendering it. So, in fact, the thing you are getting conceptually, like from an input-output behavior, you're getting at the right thing. Like the solution would be that somehow we would inform the convolutional encoder about the camera pose. That would be the solution. Unfortunately, there is literally no way known of doing that. So let me tell you intuitively what you would seemingly have to do to make the convolutional encoder do the correct thing. What you would have to do is you would have to say, okay, like, look, all of the training views that you saw at training time were like captured from some distance away. Now you can say, okay, so we zoomed in. What does that mean? Intuitively, the image will get bigger. And now what you would have to do, and we're going to talk about that in a few lectures from now, you would have to take the filters in your convolutional neural network and you would have to resample them to basically, you would have to resize the filters in a way. And if you resize the filters, which is not actually, you can't actually do this in this case, but like just intuitively, if you resized all the filters and you were really smart about how you built the convolutional neural network, then maybe you could pull it off. But if you just give the camera pose as input to the convolutional neural network, you can do that. The same exact thing is going to happen because at test time, you're just going to give a camera pose to the convolutional neural network it has never seen before. And the convolutional neural network is not actually going to discover the rule that connects the image to the camera pose. It's not going to figure that out by itself. And now the golden question, if you answered it, you might win the next Turing Award, is how would you build a neural network that you could give these two things and it would actually figure it out by itself, provably? That is, in some ways, this is the big question in both vision and machine learning more general. And the thing that we're getting at here is what you would really want is you would like some kind of neural network that in a self-supervised way would discover the structure that is in the data. And it turns out transformers are much better at this than convolutional neural networks. Why we are only starting to understand status now, you can read the most recent crop of papers at iClear, and you might get an idea for why that is. With neural networks, we have already discussed how they work. The math kind of caught up with like these neural tangent kernels a little bit. But it turns out that transformers do something different. So transformers are slightly better at this, but nevertheless, it would still not work. But we're getting there. I would bet that in 15 years, we do have a neural network that does this. But right now, it doesn't exist. So good research topic. Join my group. Okay, so encoding and auto-decoding. So like now, just for the record, right, so this is just, I made these figures some time ago. So just for the repeat, right, like there's this encoder thing where you take your image or input, then you encode it into latent code, then you predict the weights of your neural field, and then you can just use the neural field as your scene representation. And the auto-decoding that we just discussed is you just have this database of latent codes at training time, and then you auto-decode them instead of having an encoder. So that's just kind of the difference. Okay, any more questions about this topic? Like, I don't think my explanation was particularly good. Right now, I'm failing to come up with a better explanation for why. Does it intuitively make sense why this model generalizes to these out-of-distribution views now? It's basically one way of putting it. It's because the renderer is truly equivariant to the camera pose, or like the renderer is truly doing the right thing when you give it the camera pose, which is it just moves the camera around, and it moves the samples along the race around. That's exactly the right thing to do. And so from the perspective of the renderer, nothing changes. Like from the perspective of the renderer, nothing is out of distribution from the perspective of the renderer. Everything's perfectly fine. You're still sampling points in 3D space. Now your points in 3D space are at slightly different locations, but not much. Same. So the renderer doesn't care. So and that's why it still works, basically. Good. And so the big pitch here, 3D structure enables generalization to out of distribution. So like this is one way in guaranteeing that you're generalizing to out of distribution is by building structure into your model such that there is no distribution shift conditioned on the structure that you're building into your model. So here we built a renderer. If you have your renderer, then novel views aren't a weird thing anymore, so it still works. If you have a convolutional encoder only, then it fails. Okay, and so now you are fully in the picture about this paper. This is exactly what my paper was about in 2019. And back then, I was really excited about this. Obviously, in hindsight, lots of things that I didn't understand about this, but that was my whole PhD, basically. Okay, good. So here's the figures that we made for the paper back then. So scene representation networks at the top, and you can see input images, and these are the renderings. And then here you can see baselines. This is actually the convolutional encoder that we discussed before, the convolutional autoencoder. This is another paper which is well, I'm not going to talk about this, but this one is a DeepMind paper from 2018, which is called Neural Scene Representation and Rendering. And that also is just a black box thing. And as you can see now, that works. So we just already talked about the thing that this thing is now resolution independent, right? Which means that after you reconstruct the thing, because the renderer, just as with NeRFs, because the renderer is just rendering single rays. You can just shoot more rays, render the image at a higher resolution, right? So this was one of the things we showed back then as well. So this is just the car rendered at different resolutions using the same renderer. And here is actually the property that allows you to generalize to out-of-distribution views for rendering. This is kind of the dual of the inference thing that we were just discussing. So at test time, you can zoom into the car arbitrarily closely, even though in your training set there has not been a single view of a car up close. And that's because the renderer still works, right? The renderer is doing sphere tracing. The sphere tracing algorithm still works if you zoom in closer to the car, no problem. Or volume rendering still stays the same. But if you train this thing that we discussed before, and you try to give it a novel view to render it just for rendering, then it can't generate that view, because in your training set there was no such image. So of course it won't be generating an image with the correct distance now. Okay, and then here's the latent code interpolation. So here you asked about this previously. So here we're interpolating different chairs. Exciting. So this is just walking from one latent code to the other. Okay, and you can, okay, whatever. Okay, so now we're getting to this today. Exciting. So now back to the question. So you might have been semi-excited about these results because you're like, okay, these are single objects. Who cares about shape-net objects? Fair question. So far, especially insofar as so far we always discussed these, like, we saw these photorealistic 3D reconstructions and everything looked amazing. And now we're looking at this and we're like, not that exciting. So the reason why this is, of course, is because this is a much, much harder problem, right? Like we're solving a much harder problem. In the other case, we didn't do anything smart at all. There was no learning in the other case. The other case was just reconstruction. There's nothing, you didn't need to learn anything about the 3D scenes. You just needed to solve a little optimization problem for each 3D scene, or like a big optimization problem, I should say. So, so this problem is much harder, but nevertheless, the question is, why can't we do more exciting scenes? Why can we only do these shape-net scenes? And just as with autoencoders before, if you try to train this model on like data sets of whole scenes, it's not going to do anything reasonable. And now we're going to discuss why that is. One good way to think about this, one good mental framework for this, is that the thing that we were discussing so far, we call global conditioning. Let's just introduce that name. Global conditioning means that wherever you sample your 3D location, your 3D scene representation, at every 3D position, there's the same latent code. So, for instance, in our neural field case, right, we reconstructed the whole neural network from a single latent code. And so no matter where you sampled your neural network, the weights of the neural network were reconstructed always from the same latent code. There's actually a bunch of papers. So my paper was one of them, but we actually, the first ideas for neural fields came from parameterizing assigned distance functions and occupancy net fields, if you remember, we discussed this. And here's the results from these papers, and what you can tell is that all of them are single object. I mean, this is only 3 years ago. It's not even that long ago. But all of these are kind of single objects. So all of these use a single latent code for each of the objects that you see. So this bench is reconstructed, is parameterized as a single latent code. This car is parameterized as a single latent code, and this airplane is parameterized as a single latent code. Okay, so we're gonna skip this, but there's good news and bad news. So the good news is that if you look at the latent codes almost certainly have information about what kind of object is encoded in them. So for instance, if you look at these different cars, there's like some cool properties you can see that like the wheels of one car always change into the wheels of the other car, or like if you interpolate it between objects, you might also see like some cool interpolations. And what that basically means is that the autoencoder does discover information that is useful for compression. So it's like, okay, all the cars have wheels. So just by virtue of having to compress the data set, it's going to discover that the wheels are always in correspondence. And you can use this and exploit this, but we're not going to talk about it because we're going to talk about something more exciting. Okay, so the key limitation and why autoencoders don't work is because they are, by design, limited to non-compositional scenes. What does that mean? So let me give you a little example. Let's say all of your scenes had a single object in them, like a single car. What is the degrees of freedom of your data set? Like imagine, for instance, imagine for a moment you had a handcrafted generator for cars that maybe had parameters like the color of the windshield. It had a parameter like the length of the car, maybe like how big the wheels are, and so on. How many parameters would that model maybe have? Maybe a few hundred, or maybe a few thousand, right? Like most cars can be explained from the outside at least with a few hundred or thousand parameters, right? No problem. Okay, so it turns out that if you have a data set of single cars, encoding them into a single latent code, perfectly reasonable, no problem. Let's say you have a data set where you have 2 objects in each scene. So now you have 2 cars, dumb example. You now have 2 cars, so car 1, car 2. What's the degrees of freedom of the data set? That's right, whatever you just said squared, right? So like now, let's think about this. Your first car has how many degrees of freedom? Like let's say it has 1,000 degrees of freedom. That's the number of parameters you need to describe that car. But now, from the perspective of your model, right? Your model will map whatever 3D scene to one latent code, right? So now, from the perspective of your model, every time you move one of the 2 cars, it's a new scene, right? So from the perspective of your model, the number of scenes or the size, the actual literal degrees of freedom of your training set has not increased by 2 or something. The literal degrees of freedom of your training set has just increased by squared. And actually, going forward, it's going to be factorial. If you add another thing, the degrees of freedom absolutely explode, right? And you can, of course, convince yourself of this fact, like how many possible ways are there to arrange all of these chairs in this room? The number of ways to arrange these chairs in this room is humongous, huge. You could like, I don't know, there's billions of ways of doing this. So in fact, if you have even data sets that are built of these like 3 objects or 4 objects, the number of degrees of freedom that you need to store this is really, really, really large. Okay, so that's one thing. And now there's 2 ways of, let's just stick with that. Does that intuitively make sense? Okay, good. So that is why, and this is the same as the curse of, this is also, why does your neural network now fail to like, okay, what would happen if you now trained your neural network on this data set of like 2 cars? You move them around at training time, and now at test time, I give you a new arrangement of 2 new cars that the model hasn't seen. What would you expect to happen? Oh, well, okay, it's kind of lame. It will fail. It will do a really poor job at it. Even if your training set has 5,000 cars in it, or 10,000 cars, like 10,000 scenes with 2 cars, that number of training samples is tiny compared to the true complexity of your training set. Because the number of degrees of freedom of your training data is actually way larger than 10,000. It's humongously huge. And with every object that you add to your scene, the degrees of freedom just get exponentially more. And so technically, if you wanted to discover this in a dumb way from data, you would need a number of training samples that is exponential in the numbers of degrees of freedom in your training set. Does that make sense? Okay. This will actually come haunt us again in diffusion models. So when we talk about, we're going to talk about diffusion modeling, or like about generative modeling. So has anyone ever tried training an unconditional diffusion model on ImageNet? Who has trained diffusion models before? Oh, no one. Okay, never mind. No, sorry. Okay, so I see. But you all know about diffusion models, right? Everyone knows, like, I don't know, Midjourney or any of these images. Okay, how are these models trained? These models are trained by take text as input, generate image, right? Okay, so who has ever trained a GAN? Has anyone ever trained a GAN? Okay, a few more people. You have trained a GAN. So you can train GANs on like very small distributions. For instance, you can take like the distribution of faces of celebrities. It's a common data set, CelebA or CelebAHQ, right? So these are just literal pictures of celebrities, like thousands of them. I don't know. And you can train your GAN on that, and it's totally going to work. You can train your diffusion model on that, and it's totally going to work. But ImageNet, for instance, doesn't have one class of objects, like one type of data. It has 1,000 classes, or like, 1,000 classes in ImageNet, right? And so it turns out if you try to train an unconditional generative model, so a generative model that just tries to conjure up a realistic image, and you try training it on ImageNet, it's not going to do anything. It literally doesn't work. You can take the biggest diffusion model that you can build, like 1 billion parameters or 7 billion parameters, and you can train it on ImageNet, and it's not going to do a very good job at generating realistic ImageNet images. And that's because the degrees of freedom of the ImageNet dataset are actually too large for the diffusion model to capture. So the models that work, they all require text as input. They always require you to give them text, and conditional on the text, they can generate an image. But just trying to generate images by themselves doesn't work. And the reason is kind of a little bit similar to this. What you need to do is you basically need to make sure that conditional on the input of the model, the degrees of freedom of your data can't be too large. And it's a little bit similar here. It's okay. It's okay. Approximate equivalence, but like, okay, good. So how can we fix this? And we're going to talk about one paper in more detail later, but how can we fix this? We're going to fix this by being really, really smart about our encoder and about our latent space. Let me first introduce some terminology. So far we said we did global conditioning, so we had a single latent code that we decoded into our 3D scene representation. Now we're going to do something different. We're going to say that dependent on where you are in space, we're going to decode that local position in space with different latent codes. For instance, an example for this might be a voxel grid. So imagine now we represent our scene as a voxel grid, and in every voxel, we store a little latent code. Right? Just as before, we had one latent code for the whole car. Now we're going to have lots of latent codes for the car, and the latent codes are going to be arranged in a grid. Does that make sense? Okay, good. So you already know how you could then, like, for instance, render a nerf from that or something, right? You could, like, there's many ways of doing it. You could, for instance, like, you could, like here, you do trilinear interpolation. If you want to sample a 3D location, you do trilinear interpolation of the features that you have stored in the grid, and now you decode them with a tiny neural network into, like, RGB alpha or something, or the occupancy. How do you get the voxel grid? Let's say for a moment we had as input a point cloud of our scene. So we're going to work our way up. Later on, we only have images. For now, let's assume we had a point cloud of our 3D scene, right? So for instance, for our little car, we would have a little point cloud of our car. And now we want to reconstruct this voxel grid. What could you do is you could build like a neural network that decodes every voxel from the points that it contains, right? So you basically draw your voxel grid around the point cloud. And now you say, oh, the value in this voxel is going to be determined by all the points that lie inside that voxel. And you build like a little neural network that just looks at these points and then decodes, it produces a feature for that group of points. Does that make sense intuitively? You don't have to understand how you actually implement it, just on a high level, right? Okay, good. So now you can train this. For instance, you can train it on a data set as follows. Let's say you have a data set of point clouds. You can actually train a model that learns to, for instance, encode the sign distance function or the occupancy function. So you give it the model that we just discussed. It might take a point cloud as input, and then it maps it to this voxel grid via this little thing. And then you could decode this voxel grid into an occupancy function or a sign distance function. So for instance here, you could see input point cloud and output these 3D scenes, right? And note something, these 3D scenes are not single objects anymore. These 3D scenes are actually now 3D scenes, right? There's like chairs, and this should surprise you because as we just discussed, it seemed it would be really hard to like do this because apparently now the degrees of freedom of these rooms is super, super huge, right? So why does this work? Okay, let's ignore this for a moment. Why does this work? No, we're going to ignore this as well. Turns out I don't have slides for why this works because it's, no, I should. Wait a second. No. Sorry, I have a slide somewhere where I explain why this works. Aha, good. Why does this work where the previous thing failed? Let's think about this for a moment. So let's go back to our example with the 2 cars in our training set, and then I'm going to let you go after this little thing, and I'll leave you to ponder about this. So let's say we go back to our little training set where we have 2 cars for each 3D scene. And now what we're going to do is instead of having a single latent code that parameterizes the whole scene, we're actually going to make a grid. So we're going to discretize the space, right? And we're going to discretize the space. And now each voxel intuitively only has to encode information about whatever part of the 3D scene is inside of it itself, right? Good. So then let's first talk about this from the perspective of what information has to be encoded in the latent codes. So let's say, okay, so here's an example. Here's an example where you have a single object in like a 2D voxel grid, right? So what information does this voxel have to encode? It only has to encode information about this part of the object, right? Okay, good. What happens if we move this object down? Let's say we take this object and we move it a little bit. What changes from the perspective of these voxels? All that has to, imagine for instance that you take this object and you move it exactly one voxel down, right? So now all that has to change is that this voxel now has to have exactly the same information that previously this voxel had to encode, right? You basically just, in other words, if you think about the, if you think about the space of single voxels now, like the space of latent codes for each of the voxels, the space of these voxels is now much, much smaller than it was before. Because now each voxel only has to encode information about whatever is contained in it, and the set of things that can be contained in the voxel is much smaller than the set of things that, like the set of these 3D scenes that are moving around. Does that intuitively make sense? Yeah? Okay, good. So it makes sense from the perspective of the latent space, right? Now each voxel has to encode like only very, very little information, and the voxels, in fact, they don't really care. If you take the object and you move the object around, all that has to change is that now each voxel has to change its own value, but like it doesn't have to change its value as a function of the, no voxel has to encode the position of this object, right? Like there's not a single voxel in this whole grid that has to encode the object is at location xy. Instead, each voxel just has to encode whatever is contained in itself. So there is not a single voxel in here that has to encode the location of this object. Does that make sense intuitively? Okay, good. So what ends up happening is that by having done this, and there's like lots of theory on this, like this is what some of you might have heard about, like shift equivariance, or like in geometric deep learning, this is a big topic. What we have done is we have made the latent space factorially smaller. The size of the latent space now is like very small compared to what it had to encode previously. Previously, one latent code had to encode all of these crazy degrees of freedom. Now each of these latent codes has to encode like a tiny set of information, which is just like whatever surface is encoded in a tiny latent code. And now there's one final thing that is magical, because what would happen if you, in the example that we just discussed with the point clouds, what would happen if you took the point cloud and then you built an encoder that went to a single latent code and then you decoded it into the voxel grid? Would that have worked, or would that not have worked? It would have not worked. For the same reason as before, right? Does that make sense, right? So if you took this point cloud and you encoded it into a single latent code and then you just decoded the single latent code into the voxel grid, then it would have still not worked, because you have this bottleneck in there. You have this bottleneck where at some point the whole scene has to be encoded in the single latent code, and that breaks it again. Like now you still have this bottleneck in there, and you still have a mapping in there which has to go from the space of all possible 3D scenes to this tiny latent space back to the voxel grid, so that doesn't help. So clearly there's another property that we need on the encoder side. So the way we get the voxel grid has to be special as well. And it turns out the way it has to be special is it has to keep the locality alive. So for the point cloud, as we just discussed, the encoder that we had built, it took a voxel and looked at all of the points that are contained in that voxel, and that's how it figured out what to store in that voxel. That's how it figured out what features to store in that voxel. And that is the magical part. So basically, as long as it is true that in the end you have your 3D representation, which is a voxel grid, as long as it is true that you can basically trace back where in the input that came from, and you never break this locality chain, such that every voxel is always a function of a local neighborhood in the input, as long as that is true, your model will work. And the moment you break it, it will stop working. So this is not a super intuitive concept to understand. So we are at time, so I'm going to let you go. But we're going to talk about this a little bit more next lecture. And we're going to talk about how we are actually going to use this in reconstructing 3D scenes from images, because right now we just talked about point clouds. And we're going to repeat this, and I ask you to think about this a little bit more. And if you have any questions, feel free to come to the front right now. We can discuss it a little more. Thank you.